Suppose we have a sequence a sub n that converges to L. Then we know that the limit as n approaches infinity of a sub n is equal to L. Let's also consider a function f of x that is continuous at the point L. By definition, this means that f of x converges to f of L as x approaches L. Because of this, we can say that there exists an integer n such that f is defined at all values of a sub n for all values of little n that are greater than or equal to the integer capital N. Since f is defined at all values of a sub n that satisfy this condition, we can say that the sequence f of a sub n converges to f of L. This means that because f is a continuous function as the inputs a sub 1, a sub 2, a sub 3, and so on approach L, the outputs f of a sub 1, f of a sub 2, f of a sub 3, and so on approach f of L. We can use this property to find limits of more complicated sequences. Let's try an example to illustrate this idea more clearly. We want to determine if the sequence sine of the quotient 5n plus 10 over n all over 2n minus 4 over n converges. Notice that in this case, the sine function is our continuous function, and our sequence is the argument 5n plus 10 over n all over 2n minus 4 over n. First, we'll focus on the argument of the sine function. Divide both the numerator and denominator by n and take the limit as n goes to infinity. Dividing through by n gives us 5 plus 10 over n squared all over 2 minus 4 over n squared. Now we want to determine whether or not this limit exists. We can see that if we substitute infinity in for n, we essentially get 5 minus 0 over 2 minus 0. Therefore, we can see that the limit exists and it equals 5 halves. Since sine of x is a continuous function for all real numbers, we know that it is continuous at 5 halves. Using our property from the previous slide, this means that the limit of the function sine of the quotient 5n plus 10 over n all over 2n minus 4 over n approaches sine of 5 halves as n increases.